Okay, we'll begin our closed process analysis with a very straightforward problem. We have a large chunk of iron that is being heated from 30 to 300 degrees Celsius by heat coming from a reservoir known as a thermal energy reservoir. We are supposed to find the heat that is needed for this purpose, heat transfer, and the entropy generated in the system's universe. So that's what we are drawing. The universe is shown by a boundary that encompasses not only the block, but also the immediate surroundings. So this is a clear-cut, closed process problem. The system is closed and it goes from state 1, the beginning state, to state 2, let's say. The energy equation is simply delta E equals Q minus W external for any closed process. Of course, there is no work transfer. We don't see any shaft crossing the boundary, electricity crossing the boundary, or boundary work. So this equation gives us Q to be E2 minus E1. And of course, if we neglect KEPE, kinetic and potential energy, which is kind of obvious, there is no change in Ke and P in this problem. So the problem becomes m times small u2 minus u1. And if I use SL model for that, then it becomes mCV T2 minus T1. So now, therefore, Q, if I substitute the values given, 10,000, and the CV value, for that, we go open test and go for the property tables and common solids and liquids. The SL model is as you can see, the first row, and find iron, and that gives us a value of 0.45. And the temperatures are given 330 T2 and T1, and this becomes 1200. Is a large amount, 15,000 kilojoules, or 1215 million joules. Large numbers in SI units are converted like that by a factor of 3. So the question is, obviously the block is huge. 10,000 kg means about 22,000 pounds. So you understand immediately this is a heavy block. But how about this energy? How big is that energy? Always remember to use the benchmark we talked about in chapter 0. So if you burn 1 kg of gasoline, if you recall, how much heat will be released? That's about 45 million joules. A large cookie in your favorite store probably has a 400 calorie, which means 400 kilocalorie really, and that is about 1.67 million joules. You can show that. So that gives you a perspective in this problem that, sorry about this mess, that the amount of heat needed is really tremendous. You have to burn so much gasoline just to get that much amount of heat out. Okay, let's now do the entropy analysis again. Entropy analysis tells us that the equation is simply this. The change in entropy of your block of the system's universe is given by the amount of heat that the amount of entropy that enters through heat plus the entropy that is generated by friction in the system's universe. So therefore, we are after this quantity, changing side, delta S minus Q over TB, and that's mass times S2 minus S1 minus Q divided by TB. Again, using the SL model, change in entropy is given by this formula. You can go and check. Again, you can open table J and you will find the formulas there for the SL model. If we write down all our numbers, now T2 is 300 plus 273. It's important to put that in Kelvin because otherwise the formula will not make any sense and you'll get all wrong number. Sorry, this 1215,000 divided by the boundary temperature. What is the boundary temperature we should be using? Look, the boundary passes through the reservoir, which is a temperature of 1000 degrees Celsius. Okay, and this is 1215,000. So if we calculate this number, it turns out to be about 1912 kilojoule per Kelvin. So there we have it. We have solved the problem theoretically. Let's quickly check the answer using a test calc.